Since time immemorial, humankind has looked to the stars. The universe has always been a source of fascination and of mystery. How was the cosmos born? What else might the universe contain? And where do we come from? The furthest reaches of the universe now seem closer than ever before. Telescopes and probes allow us to peer even deeper into the universe, analyzing primordial light with ever greater precision. New images and the latest research are fascinating, but they also give rise to new questions. Where did the universe start, and where does it end? And what exactly is the light emitted by stars? Welcome to Spacetime, featuring astronaut and scientist Ulrich Walter and an expert on surprises the universe has in store for us. Light is energy. Without our sun's energy, nothing could exist, at least not in our solar system. But our sun is just one source of energy amongst many in the universe. There are 100 billion stars in our Milky Way. Each of those stars has its own history and its own story to tell. It is those secrets that scientists hope to unlock. Today, researchers are gazing ever deeper into the universe, exploring the mysteries of dark and light.
So, what is light? St. Augustine would have put it like this. If no one asks me, I know what it is. If I wish to explain it to someone, I don't know. So the answer is rather tricky. A physicist would say, light in a vacuum is the excitation of space. That sounds complicated, and it is. But generating light is relatively easy. Usually it's done like this. I heat matter, which could be a gas or solid. That excites its atoms, and they then emit light. Light exists in a variety of forms. There's infrared light, visible light, that's what we see. There are also other kinds of light, such as ultraviolet light, X-rays, gamma rays. Physicists have also discovered that light is a wave, just like a surface wave. That's why light travels. Light moves. And light has a speed that is finite. It originates somewhere, travels, and arrives where we are. So that means that the light we can see tells us the story of the time in which it was born.
The European Southern Observatory, or ESO in Chile, offers an unparalleled view of this past. Here in the Atacama Desert, more than 2,000 meters above sea level, the Earth's atmosphere no longer obscures the view into the heavens. Since 2013, the 66 telescopes of the ALMA project have been exploring the universe, much to the delight of astrophysicists.
We have images made with the best millimeter telescopes prior to ALMA, and all you see is a blob. But with ALMA, for example, you can see an amazing ring. Every new telescope, technology, and instrument for capturing data ends up turning our understanding on its head. That's why we keep progressing, and I don't think that will change.
At ESO's La Silla Observatory in Chile, astronomers have already been able to determine the motion of 14,000 sun-like stars in the vicinity of our sun. Stars appear brighter here than almost anywhere else on Earth. Elsewhere, light pollution makes it difficult to see even the Milky Way with the naked eye. In Germany, the best places for stargazing are the dark sky reserves, which restrict the use of artificial light. On cloudless nights under a new moon, stargazers flock to the Rhön Star Park and the Westhaveland Park outside Berlin for a clear view of the night sky. This darkness and the natural spectacle of the stars has become increasingly rare. Gazing up at the starry sky, we are struck with the realization that our Earth is little more than a speck of dust in the endless expanse of the cosmos. When we look up at the heavens, the light we see is millions and even billions of years old. The celestial bodies that emitted this light might not even exist anymore. As darkness is vanishing, people are increasingly seeking out places where they can see the stars. We are becoming increasingly aware that the night sky is part of our cultural heritage, a natural resource we should treasure and preserve.
Our universe is almost infinitely large, but the number of points of light on the firmament is finite. That's what we can see with our telescopes. That's what we call the visible universe, which is made up of 100 billion galaxies. One of those galaxies is our Milky Way. So, how many stars are there in a galaxy? Well, on average, it's about 100 billion. What a coincidence. 100 billion. How many is that? Well, it's roughly the number of grains of sand in 1 cubic meter. So, how do we count something like that? Well, astronomers have a very simple method. They extract one portion, meaning they look at one section of the firmament and then count the number of stars in it, just like you might count the grains of sand right here. Then they extrapolate that to the entire cosmos. That's how it's done. By the way, here's another lovely coincidence. Our brain is made up of about 100 billion neurons. So you could say our brain is a miniature cosmos.
Insofern ist eigentlich unser Gehirn ein kleiner Kosmos.
In Chile, radio telescopes are being combined into a powerful array on the ground, but telescopes have also been sent into space. By the 1970s, these telescopes could also observe light in the ultraviolet and infrared range. The ESO is headquartered just outside Munich. For astrophysicist Susanna Randall, light is central to her work.
When it comes to the kind of light we see outside, of course we want as little of that as possible when we are observing the stars. But the information we receive from the stars, the galaxies, exoplanets and so forth, all of that is also light. For physicists, light is electromagnetic radiation of varying wavelengths. The light that's visible to us with our naked eye is just a small fraction of that electromagnetic spectrum. In other words, in astronomy we are utterly dependent on light. Without light, we quite literally would not be able to see.
Our rather unassuming planetary system is located in the midst of that conglomeration of light. At its center is our Sun, the star whose energy has been powering our planet and the life on it for billions of years.
When we observe the Sun, for example, the light that comes from the Sun is 8 minutes old. When we observe the oldest galaxies, that light can be as old as the universe itself. That's almost 12 billion years old. So it's very old light. When you consider how big the universe is, how old it is, it's more than a human brain can comprehend.
Alpha Centauri, the star system that is our Sun's closest neighbor, is about 4 light-years or 40 billion kilometers away. But many other stars are not so easy to locate.
We need all of the wavelengths of light to truly understand the universe. It's like when you have a black and white photo. You can see the contours, but a lot of information gets lost. When you only observe the universe in the visible range of light, you miss everything in between. You'll see the stars, but maybe not the surrounding dust. Then you won't understand how those stars were born. That's why we have telescopes that operate at various wavelengths, which allow us to observe the invisible universe.
ESO also has other big plans in store. In 2023, a new super telescope in the high plateaus of Chile is scheduled to go into operation. It will be able to observe light in the visible and infrared range in search of what is called hot matter. But will the light of the universe extinguish one day?
Right now, we have electromagnetic radiation in all wavelengths. But eventually, the stars will die, and then we won't have any more light here on Earth. We'll still have low-frequency background radiation, the cosmic background radiation we already know. But eventually, light as we know it won't exist in the universe.
For now, plenty of light still reaches us here on Earth, and we continue to search for ways to transform the sun's light into energy.
Light, or more precisely, light particles, are pure energy. They have no mass at all. We'd like to be able to use that energy to produce electricity. There are two possible ways of doing that. Directly with solar cells. That's relatively easy, but it's not terribly efficient. The other option is using what are called solar generators or solar power plants. What you do there is heat water. The steam it generates is then sent to turbines, which then generate electricity. That's more complex, but also much more efficient.
Almeria province in southeastern Spain is home to Europe's biggest test center for concentrating solar power. On the 100-hectare site, researchers are exploiting the full force of the Andalusian sun to test and optimize high-temperature solar technologies. More than 20,000 differently shaped mirrors can be combined into specific formations to generate extremely high temperatures. In this way, the solar radiation can be concentrated up to 1,000-fold. The solar research facility was developed in partnership with the German Aerospace Center. The technology developed here is now being used around the world. More than 90% of solar power plants worldwide now use this technology.
Another unusual characteristic of light is that it's a wave. Those waves can be modified, or at least various properties of those waves can be modified, like the amplitude or phase. That's called modulation, and we can use that to transmit information. Take this example. Here we have a laser, which generates a beam of light. Now the simplest way to modulate it is switching it on and off.
Laserstrahl an und aus.
Each time I switch it on and off is equivalent to 1 bit. I can do that very fast, more than 1 billion times a second. That's what beaming technology is based on.
Beam me up. The crew of the Starship Enterprise made teleportation look simple. In real life, it's a good bit more complicated. Light can be perceived as tiny particles called photons. Two particles can be linked in an interdependent quantum state, no matter how far apart they are. This phenomenon, also called quantum entanglement, can also be used for teleportation. Physicists have already used it to transmit information from La Palma to Tenerife. An even more spectacular experiment was carried out by Chinese scientists. For the first time ever, they succeeded in teleporting from the ground to space. Working out of a base station in Tibet, they teleported a photon to a satellite in near-Earth orbit, 1,400 kilometers away. But the researchers could only recover 1 out of every 6 million photons that were transmitted.
The closer we get to the speed of light, the further we travel in time. What does that mean? To understand that, we have to understand a bit about the theory of relativity. But don't worry, I'll keep it simple. This part is important. Einstein said that the time that I experience, regardless of where I am or how fast I travel, always moves at the same pace.
Tick, 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 tick.
But someone observing me would see my time passing at a different rate. In turn, I'll observe the passage of time in the outside world differently. Let's imagine an external observer on Earth watches me through a telescope and sees my clock. I'm an astronaut on a rocket. So what would that observer see? They would see my clock tick more slowly.
Tick, tick, tick.
In other words, compared to their clock, my clock is moving more quickly. I travel at close to the speed of light, heading to a star, and then return. Let's say 1,000 years have passed for my observer, but only something like 10 years has passed for me. I'll be landing in the future of my observer's time, in the future, back on Earth. The faster I travel, the further into the future I'll go. That's the essence of the theory of relativity. That's why Einstein says we can always travel to the future, but never to the past.
The faster you travel, the slower time passes, and the slower you age. Traveling at the speed of light, no time would pass at all, or so says Einstein's theory of relativity.
One of the central discoveries of humankind is that the speed of light is finite. It's fast, 30,000 kilometers a second, but finite. For a long time, people thought, well, light arrives immediately, so the speed of light must be infinite. But if that were so, it would have dramatic consequences. Space and time would be completely decoupled. You'd have time on one side, space on the other. Instead, light takes a finite amount of time to travel from one point to the next. And any type of data also takes a finite amount of time to get from point A to point B. The speed of light is why space and time are linked. That was one of Albert Einstein's central insights in his special theory of relativity of 1905. The entire structure of our universe and the way we discover and investigate the universe is based on that.
The speed of light appears the same to all observers, no matter how fast that observer is traveling. That's a key point of Einstein's theory of relativity.
The speed of light shouldn't be equated with time itself. Light takes a certain amount of time to travel a certain distance. The speed of light is the intermediary. Say I look at a star, Alpha Centauri, and the light's taken 4 years to reach me. I see the star the way it looked 4 years ago. So the speed of light is the delay that results from those 4 years. This delay happens because the star is located 40 billion kilometers away, 4 light years. The speed of light establishes the relationship between time and space.
In 1985, the German-led D1 mission on the Challenger space shuttle carried out extremely precise measurements to test this basic theory of physics. On what would be the last orbital flight of the shuttle before the 1986 disaster, the astronauts, among them the German payload specialist Ernst Messerschmitt, monitored the deviation between a clock in space and on Earth. These experiments would later help with the development of GPS satellite navigation technology. For the first time ever, the scientific mission was monitored by the German Control Center in Bavaria. The shuttle crew's mission lasted a total of 7 days, 54 minutes and 51 seconds. On landing at Edwards Air Force Base, the results confirmed the clocks didn't operate differently in space. Time itself moved more slowly. The crew was younger than they would have been had they remained on Earth, if only by 0.2 milliseconds. The ultra-precise Faro atomic clock will further test this theory. This clock is only 1 second off in 300,000 years. Attached to an external pallet on the Columbus module outside the International Space Station, Faro will test Einstein's theory of general relativity with unprecedented accuracy. Using microwaves, Faro will communicate with ground stations, allowing for the ongoing comparison of time in outer space and on Earth. Einstein said time on a moving spaceship depends on speed. The faster it travels, the more slowly a clock on board will move relative to the external observer. 12 seconds on a stationary spaceship is 9 seconds on a spaceship traveling at close to the speed of light.
We want to know more about our universe, and that means observing ever more distant galaxies. But as they grow further away, the light we see is weaker, and they appear smaller. That's why our telescopes keep getting bigger. As the aperture of the telescope gets bigger, the amount of light we collect increases too. As the telescope's beam path grows longer, the image we see becomes more precise. Galileo couldn't actually see all that much through that very first telescope. His telescope was only about this long and the aperture was only about this big. That was just about enough to see the moons of Jupiter. Today we have gigantic telescopes, which provide us with very sharp and clear images. We can even see light that's not visible to the naked eye, meaning light in the infrared and ultraviolet range. But there's another problem. Our telescopes here on Earth have to cope with the fluctuations of our atmosphere, which create a blurry effect. To bypass this atmosphere, we send telescopes into outer space. The Hubble telescope is probably the best-known telescope in outer space.
NASA's Hubble Space Telescope made history. Thanks to measurements taken by Hubble, we now know our universe is expanding even faster than we thought. Here on Earth, scientists have only an imperfect window on the universe. In outer space, free of the distortion of the Earth's atmosphere, the images provided by the Hubble are exceptionally clear.
Our go for main engine start, T-minus 6, 5, 4, 3, 2, 1, and liftoff of the Space Shuttle Discovery with the Hubble Space Telescope, our window on the universe.
In 1990, the Space Shuttle Discovery brought the Hubble Space Telescope into orbit, but soon scientists realized that the observatory's main mirror had been ground incorrectly. The image quality was far lower than expected. A repair mission in 1993 finally brought high-resolution images. The Hubble has provided a transformational view of the celestial bodies and phenomena that make up the universe, capturing everything from planets and exoplanets to stars and cosmic nebula to black holes and distant galaxies, all in images of stunning brilliance. The next generation of observatories is already under development. The James Webb Space Telescope, which cost some $9 billion to build, promises even better images. Unlike the Hubble, it will be launched into an orbit 1.5 million kilometers away from Earth.
The diameter of the Hubble telescope is 2.2 meters. The diameter of the James Webb is around 6 meters. It's bigger and will deliver images that are 3 times as precise. Unlike the Hubble, it won't orbit the Earth. Instead, it will be positioned behind the Moon, with the Sun, the Earth, and the Moon remaining along roughly the same axis. So the Webb won't have to deal with as many fluctuations of light. The Hubble always flies through the shadows of the Earth into the sunlight and then back again. Over the course of a year, the Webb will observe the entire heavens. Its spatial resolution is much higher, and it will be able to look deeper into the infrared range. That's interesting because the more distant galaxies are getting redder. They're very old galaxies, very far away, and most of their light is in the infrared range. We hope the Webb will let us see galaxies that are much further away than we've been able to observe through the Hubble.
Scheduled for launch in 2021, the Webb will be the most powerful space observatory to date. By looking at the planets outside our solar system at a range of wavelengths, it will provide researchers with a trove of new information.
Astronomy got its start in the visible range. Early telescopes all operated in the visible range. It's the most obvious range for us, since it's what allows us to observe objects directly. Astronomers could look into those early telescopes and actually see something. These days, our telescopes can cover nearly the entire electromagnetic spectrum. But from here on Earth, we can't see certain ranges, like UV radiation, for example. For that, we need to go into outer space. Fortunately, here on Earth, our atmosphere protects us from that kind of light.
Our observatories continue to grow ever more sophisticated.
5, 4, 3, 2, 1, 0. Liftoff of the mighty Delta IV Heavy rocket with NASA's Parker Solar Probe, a daring mission to shed light on the mysteries of our closest star, the Sun.
The Parker Solar Probe has to overcome obstacles that space engineers long believed were insurmountable. First and foremost, the probe has to be able to withstand blazing heat. Over nearly 7 years, its orbit will gradually get closer and closer to the Sun. In late 2024, it will reach its closest pass, braving extreme heat to touch the corona of the Sun.
The solar telescope has two major differences compared to a normal astronomical telescope, which operates at night. First, the sun is bright, which means the telescope doesn't need to collect as much light as possible. The sun provides the light. Unfortunately, a lot of light means a lot of heat. And that means the telescope will heat up, it will warp, and the image will get blurry. So you have to get rid of that heat somehow. That's why solar telescopes have special devices for getting rid of that heat and making sure the images stay nice and sharp.
Researchers first began pondering how to design a probe that could approach the Sun in the late 1950s.
Engine start. 1, 0.
The Parker Solar Probe will certainly not be the last device that we launch into the solar system and beyond. As technology gets increasingly sophisticated, our thirst for knowledge about the Milky Way and the rest of the cosmos grows apace. Our curiosity about the stars and the planets and what they are made of appears unquenchable, as vast as the universe itself. To satisfy that curiosity, no effort or expense is being spared. But astronomy can also take place in the stratosphere. Mounted on a converted jumbo jet, the SOFIA telescope conducts observations at infrared wavelengths. Its data will help unravel the mysteries of new stars and galaxies and the dust clouds that give rise to them.
The detectors on this telescope that are sensitive to thermal emissions are comparable to heat sensor cameras that people use to see if their homes are leaking heat. They can look deep into those dirty clouds and see what's happening inside them.
The measurement process sounds straightforward.
We tune or set the instrument just like you might set the radio to a certain station in the morning. We want the spectrometer to be set to a frequency that will make it receptive to whatever astronomical phenomenon we hope to observe.
An idea that worked.
Almost all the light in our universe is generated by heat. The best way to illustrate this is with this candle. When I light it, the wax burns by consuming oxygen in the atmosphere. That's not quite how it works in stars, but in any case, the process generates immense amounts of energy. That energy and heat activates the atoms in the flame. Not the gas atoms, though, but the soot, which is at the top of the flame. The heat makes that soot glow. That's the light we see coming from the candle. Light bulbs operate according to the same principle. The electricity flows through a filament. Electricity is comprised of electrons, small particles. Those small particles rub against the atoms, activate them, and cause the light bulb to emit light.
The natural cycle of day and night has been disrupted. On the International Space Station, the sun rises every 90 minutes. Darkness is in short supply. The view from the ISS also shows how brightly illuminated vast parts of the Earth are at night. This artificial light has a dark side. In recent years, we have become increasingly aware of the problem of light pollution, caused by an excess of artificial light. The reflected light scatters in the atmosphere, heightening the effect. The glow creates a luminous fog, resulting in light domes that can be seen from afar.
Light and darkness are distributed rather unevenly on Earth. It depends on the latitude. Take the polar regions. In the summer, it's light 24 hours a day. In the winter, we have 24 hours of dark. For us humans, that often doesn't matter. We have our biorhythm, or circadian rhythm, which lasts between 24 and 25 hours. When we're tired, we sleep, and it doesn't matter if it's light or dark outside. But what about on the space station? Well, there they try to maintain the normal circadian rhythm. They divide the day into 24 hours. 8 hours of sleep, 8 hours work, 8 hours leisure. When they sleep, they turn off the light. Otherwise, it stays on. Even if the others are still out there working, when it's time to sleep, they go into their cubby, close the door, turn out the light, and sleep.
When we spend days or even months in a spaceship, what happens to sleep? Is the sleep issue something that astronauts on a space station can grow used to?
Die Schlafdauer von Astronauten ist sehr kurz.
Astronauts don't sleep much.
Seit dem Beginn der bemannten Raumfahrt.
That's been a problem since the beginning of manned spaceflight.
So eine größere Untersuchung der letzten Jahre.
A larger study of missions on the ISS and on the Space Shuttle has shown that astronauts sleep only 6 hours a day on average.
Knapp 6 Stunden schlafen. Von Untersuchungen auf der Erde wissen wir, dass
From studies conducted here on Earth, we know that's not really enough to maintain peak performance.
Von dem her
That's why it's a problem.
Ist das ein Problem. Es ist auch so, dass der
Astronauts take a rather large amount of sleeping pills. Sleep aids are generally the most important or second most frequently used medication during spaceflight.
Das Medikament, das in der Raumfahrt benutzt wird.
Sleeping in space is trickier than one might think. We humans aren't designed to sleep untethered, floating in zero gravity. On the ISS, astronauts use a simple trick to help them sleep.
Auf der ISS,
On the ISS, astronauts live under conditions of artificial daylight.
Die Astronauten leben auf einem 24-Stunden-Tag.
They maintain a 24-hour day.
Man hat gerade jetzt im
Over the past year or so, we began installing new light sources that incorporate some of the findings of recent research.
Ergebnisse der modernen Lichtforschung hat man da eingebracht und jetzt neue.
So now astronauts are living in sync with a natural 24-hour daily cycle and rhythm.
Natürlichen 24-Stunden-Rhythmus leben.
A cabin or a sleep module where astronauts can rest might suffice on the ISS, but on the long-term missions of the future, astronauts will need to do more than just tuck into a tethered sleeping bag and turn off the light for a few hours. Imagine a 6-month journey to Mars. On such a long voyage, how will astronauts sleep? How will they survive? Could a form of induced torpor be the answer? A kind of suspended animation would allow astronauts to consume far fewer resources and arrive rested. But humans are not designed for hibernation.
Man hat sich schon Überlegungen gemacht, ob sowas möglich wäre für
We have considered whether something like that might be possible for long-term missions.
sparen, die Menschen nicht
It would reduce energy
soziale
and
Isolation.
oxygen consumption,
Allerdings,
and it would cut down on the length of time people spent in social isolation.
man hat
But humans don't really have a torpor state.
längere Phasen
We found that humans can withstand longer phases of low body temperature,
man kann das sicher
but
nicht
that's
leisten.
not really the same thing as torpor.
A 6-month journey through space would be an enormous strain for both body and mind. While an induced state of sleep would be ideal in many ways, it also poses enormous risks.
Wenn so jemand in einem torporähnlichen Zustand wäre,
Someone in a torpor-like state
quasi geweckt,
couldn't simply be woken up or brought out of that state from one moment to the next.
sicher in Notfallsituationen, gerade jetzt
In an emergency, that would be a problem.
sicher ein Problem.
On a longer mission, that would certainly be an issue. And we have no idea whether memory or other faculties might be negatively affected.
Funktion oder sowas stören könnte.
Way back then, before artificial light was invented, everything was so simple. The days were light, the nights were dark, at least during the new moon. But nowadays, or so astronomers tell us, we're polluting the dark because astronomers need darkness to observe galaxies that emit hardly any light. That's why they head out into very remote areas, high in the mountains, areas that are largely uninhabited. For example, on islands in the middle of the ocean or in remote desert regions.
The Earth also glows at night, but the spectacular play of colors of the northern lights is an exception. Most of the light at night is man-made. Over 150 years, the brightness of the night sky over Berlin, for example, has increased tenfold. Nature, too, is increasingly out of sync. In the summer, a single streetlight spells the end of 150 insects every night. Plant growth and the migration of birds are also affected.
Light pollution is an issue in cities nowadays. People who want to observe the heavens want it to be as dark as possible, of course. It's no coincidence that the ancient Babylonians could see all sorts of things in the heavens that are no longer visible to us. Back then, our surroundings were darker. Today, light pollution is a real issue. For example, insects orient themselves with the sun as a reference point. When an insect suddenly sees a bright light at night, it thinks it might be the sun. That disrupts the insect's orientation system. It's why you find dead insects near bright lights. And it's a problem for other animals, too. Many animals are confused by artificial light. For an animal, light means day, dark means night. So when an animal suddenly encounters a bright light at night, it disrupts their natural cycles. Light pollution is a real issue.
Although streetlights and artificial light are very practical, light pollution interferes with our observation of the heavens. It also has a negative impact on our well-being. 80% of the world's population live under light-polluted skies. In the United States and Europe, it's 99%. Too much artificial light can also affect our hormone levels. Researchers are investigating a possible link between nighttime light exposure and breast cancer. A good night's sleep in the dark is growing ever harder to come by. In 2007, the International Astronomical Union and the International Lighting Commission took up a battle against light pollution. They advocate a more sparing and targeted use of light. The natural cycle of day and night will never be restored, but reducing light pollution would have immense benefits for both humans and the natural environment.
Licht ist eine absolut faszinierende Sache.
Light is fascinating.
Licht ist
As a physicist, I would say light is the thing physics understands best.
gleichzeitig.
But at the same time, it's one of the hardest things for us to make sense of.
Wie passt das miteinander zusammen?
How can both of these be true?
Experimente durchführen.
Well, we can conduct experiments. We can conduct experiments with breathtaking precision. We can measure certain physical properties down to 10 decimal places.
Physikalische Theorie und können alle
We'll devise a theory that explains it, down to all 10 decimal places. So that theory must have a lot of truth to it. And yet, light is a mystery. It's both a wave and a particle. In some experiments, light acts as a wave. In others, as a stream of tiny particles. So which is it? A physicist would say both, which makes no sense. But it doesn't have to make sense. As long as physicists can explain what's happening in their experiments with a high degree of precision, they're happy.
Distant stars and galaxies continues to exert its pull. The beauty and mystery of light captures our imagination. But the light that is visible to us, the light that astronomers can observe through their telescopes, is little more than the tip of the proverbial iceberg. There are endless sources of light in unexplored corners of the universe. Moreover, the universe contains far more dark matter than it does visible matter. Only about 16% of matter is visible matter: the Earth, the Sun, the planets and stars. The remaining 84% is dark matter. Scientists still have little idea what it's made of, but at least the stars have begun to divulge some of their mysteries.
Stars aren't just spheres of gas. They come in various colors, and they have various histories. The first way to classify a star is by age. How old is it? When was it born? In the early universe, there was only hydrogen and helium and a bit of lithium. Stars were being formed out of just those three elements. Population 1 stars, which are relatively young, contain a relatively large amount of metals. Astronomically speaking, they're not very old. Population 2 stars are older. They've been around for a while and have fewer heavy elements. These are the kinds of stars we have in our Milky Way. Population 3 stars are even older than that, but we're still working on finding them.
Since ancient times, humankind has been looking to the stars and trying to interpret their celestial movement. Over the past 80 years, astronomers have been able to accumulate a vast store of knowledge about the cosmos. For example, we know that we live in an expanding universe. Until 1929, most astronomers believed that the universe was static. Then astronomers discovered that distant galaxies are moving away from us. The further away they got, the faster they seemed to move. The expansion of the universe also implies the existence of a point of origin, the Big Bang. Research has continued apace. Today, astronomers are able to make increasingly sophisticated predictions about the future of our solar system. Day by day, scientists are gaining new insights into distant stars and galaxies. But each new insight gives rise to new questions. Light from the distant corners of the universe continues to fascinate both amateur stargazers and specialists. Astronomy, the investigation and the study of the universe, is more exciting than ever before.
Astrophysics is at a golden age. New discoveries are coming thick and fast. We know today that our picture of the universe is anything but complete. We know that everything around us, stars, planets, and people, seems to make up only 5% of the universe. Then there's another 25% which we know exists, what we call dark matter. We can see its effects. but we don't really know what it is. Its origins are still shrouded in mystery.
Da liegt wirklich der Ursprung im Dunkeln.
Darkness on Earth is far easier to explain. It's simply the absence of light. Nowadays, many people and even entire countries have realized that an overabundance of artificial light is a problem. Some countries and regions have even enacted laws or regulations designed to preserve the night sky. Like Chile in 1999 and Italy and the Czech Republic. Slovenia's laws on light pollution are particularly strict. The International Dark Sky Association has listed some 40 locations that ban artificial light at night. The awe-inspiring images from the Hubble Space Telescope have also sparked new interest in the universe. The portraits of distant stars and galaxies provided by the Hubble inspired people around the world. These images reveal a strange and beautiful cosmos, billions of kilometers from Earth. These strange and beautiful images of the cosmos, provided by international space agencies, have brought the furthest corners of the universe into our own cosmic backyard, turning a growing number of us into stargazers. On a clear, dark night, some 6,000 celestial bodies can be counted in the night sky, a glittering ocean of stars, nebulae, and the planets of our solar system. Even a relatively simple telescope transforms the distant twinkle of the night sky into a dense web of light. What we see on Earth today is the light of millions of years ago, light that might long since have been extinguished. The name given to our galaxy derives from an ancient Greek myth. According to one legend, the heavenly firmament was created by the milk of the goddess. For the naturalist and explorer Alexander von Humboldt, our Milky Way was an island universe. Today we know it is one of the larger galaxies, home to an estimated 300 billion stars.
Light is important because light is pure energy. We need energy for life. Without light, there is no life.
Restoring the balance between light and dark, analyzing and decoding unimaginably ancient light. The mysteries of light will continue to occupy us for generations to come. Observing stars is a form of time travel. They transport viewers to the history of the universe. Even now, the night sky is more fascinating than the brightest city.